Let's talk about a reaction called the Claisen condensation. And it is a reaction that depends upon the use of an ester enolate. So this is an enolate reaction we never saw with ketones and aldehydes, and it's kind of specific to esters. So we're going to draw the full mechanism out here. So let's start with the reaction. We're going to take an ester, and I'm going to treat it with a base, like sodium ethoxide. And note that we're going to have to match the O-ethyl of the base to the O-ethyl of the ester, not specifically O-ethyl, but whatever the R group is, OR. And then we're going to need a second step where we treat it with a little bit of acid and water. What we're going to get out of this reaction is something called a beta-ketoester. Why do they call it a beta-ketoester? Well, here is our ester, there's alpha, and there's beta. So it's a ketone in the beta position relative to an ester. Okay, so how does this work? We are going to take our ester, and it's going to react with sodium ethoxide. And we'll pluck off that proton. That will give us an ester enolate. Now remember, esters aren't very acidic, so even though we drew this reaction going forward, in fact the equilibrium strongly favors the backwards reaction. So we just get a little bit of this ester enolate. So when this enolate forms, there's going to be a lot of unreacted ester floating around. So this enolate, which is a nucleophile, is going to say, I want to attack an electrophile, and the best electrophile it's going to be able to find is ester that hasn't been deprotonated yet. I don't think that classifies as cannibalism, but it's kind of, it's attacking itself. So we're going to attack a carbonyl here in this reaction. Anytime we attack a carbonyl under basic conditions, we form a tetrahedral intermediate. And it's hard to remember all the pieces, but here is the carbon we're attacking. And so we get an O-, the O-ethyl is still there, the methyl group is still over there. Everything's present. So for our tetrahedral intermediate, what happens? Well, we can either protonate, which we could do, or we can look for a leaving group, and with acid derivatives, we just attack an ester, it's an acid derivative, we typically think about kicking out a leaving group, in this case the OR group. I'm going to go back down to the bottom left and restart our scheme. And what do you know? That gives us immediately our beta-ketoester. And you might say, great, we're done. No, we're not done. If you notice up top, we have a second step, and there's a reason why we need that. We form this beta-ketoester. It turns out beta-ketoesters are really acidic. And so we form this very acidic molecule in the presence of base. So what happens is our base goes ahead and deprotonates our acidic ketoester product. And it forms this stabilized enolate. And that's where this first step stops. We form this enolate. That's why we need a second step. And our second step is, something like HCl and water. Is typically very dilute. Got just enough acid to make a little H3O+ and to protonate our deprotonated product. And that gets us back to a neutral compound. And this is our beta-ketoester formed through the Claisen condensation. And these reactions normally occur where one ester, in the upper left, one ester actually ends up attacking itself. So you put together two of the same molecule. And so we get our beta-ketoester as the Claisen condensation.